Ha ha ha. You made it back. Welcome to the video on separable differential equations. You've been watching the series, hopefully, on differential equations and have figured out what they are. And well, we'll talk about one common technique that we'll use to actually figure out what the original function is. Now, you're not going to be able to know everything there is to know about this because, number one, there's techniques that you'll see in Calculus 2 later on that will help you solve differential equations. But beyond that, there are whole courses on how to solve differential equations. Your curriculum only requires you to kind of study one particular technique, which we call separable differential equations. So I'm only going to show you 3 examples, but they're going to be in depth, and we're going to see exactly how we might go through and try to figure out what the original function was given a differential equation. So here we go. A separable differential equation is one where the x and y parts can be separated and integrated by each part. Okay, so some examples of ones that are separable often involve division or multiplication. So dy dx is equal to y over x can be separated into x's and y's. Dy dx is equal to xy squared over 3. Dy dx is equal to x times y. All these are separable differential equations because we'll be able to either divide or multiply by x or y, or some variation of that in order to separate our particular sides into x's and y sides. Now, differential equations that are not separable include dy dx is equal to x plus y. Dy dx is equal to sine of xy plus 2x. So notice that we can't actually just separate the x's and the y's. I'm talking about the dy's and the dx's as well. All right, in either of these cases, because they're so intermixed with each other, there's no way to actually get the x's and y's by themselves. So here's an example. Let's say that you have the differential equation dy dx is equal to x times y, where y of 1 is equal to negative 2. Find a formula for the original equation. Well, the first step that we want to do is we want to separate the variables by moving all the terms with y on one side and x on the other. And this will look a lot like the idea of cross-multiplying. It's not really what we're doing, but kind of have the idea that what we're doing is we're saying, all right, y times dy has to equal to x times dx. And yes, you can separate the dy dx part, all right, even though it's really kind of one big monstrous statement about the slope. All right, it's all about change in y over change in x, so those can be separated here. So y dy is equal to x dx. Your next step is that you want to integrate both sides. All right, so we're going to integrate the first left side with respect to y and the right side with respect to x. And we only need to add 1 plus c per side because, well, technically you really do add 2 plus c's, one on the left and one on the right, but they're both constants. So we're going to eventually subtract one of those constants over anyway and make it a new constant. So why not just avoid that step and just call it one big plus c altogether? And convention tells us that we want to write it on the right side. That's just kind of the way that it usually works here. So we say y squared over 2 equals x squared over 2 plus c. Now, if we have an initial condition, we can plug in our x and our y value. So x is equal to 1 and y was equal to negative 2. So I plug in negative 2 for y and 1 for x. All right, and when I do that, I get negative 2 squared over 2 equals 1 squared over 2 plus c. So 4 halves equals 1 half plus c, and then c is equal to 3 halves. So once you do that, we're going to, in our last step, solve for y. But we're going to make sure that we actually create a function, and you'll see what I mean in just a second. So now we know y squared over 2 equals x squared over 2 plus 3 halves. All right, so in this case, if I'm going to solve for y, what I can do is I can multiply both sides by 2, and I get y squared is equal to x squared plus 3. Solving for y allows me to take the square root of both sides, plus and minus the square root of x squared plus 3. And we want to choose the negative branch because y of 1 is equal to negative 2. And you can always check your work, by the way, by, first of all, taking the derivative, which I won't do here. But you can also plug in your initial condition and make sure that that checks out as well. So in this case, when I plug in x is equal to 1, I get 1 squared plus 3, which is 4. And then the square root of that is 2. And since we applied the negative, we get negative 2. And that's what our initial y value is when x is equal to 1. All right, so in all of these cases, we have figured out what our total derivative is. All right, example number 2, use separation of variables to solve. Dy dx is equal to negative xy squared over 4 for y is not equal to 0, and where y of 5 is equal to 2. All right, so what do we do here? First step, separate. So in this case, I want to do that cross multiplying thing, and so we get 4 dy is equal to negative xy squared dy, or negative xy squared dx. And I want to get all my y's on one side and all my x's on one side. So I'm going to divide both sides by y squared. So I get 4 dy over y squared is equal to negative x dx. All right, so all together I've got all my y's on my left and all my x's on my right. And I'm going to integrate both sides with respect to their respective variables. So remember 4 over y squared is the same as 4y to the negative 2. The antiderivative of that, when you work it out, is negative 4 over y. The antiderivative of negative x is negative x squared over 2, and then plus c. Now we plug in our initial condition. In this case, y of 5 is equal to 2. So I plug in x is equal to 5, and I get negative 25 halves plus c on the right side. And my y is equal to 2, so I get negative 4 over 2, which is negative 2 here. Solving for c, I get c is equal to 21 over 2. All right, so our last step will be to solve for y. So we have negative 4 over y equals negative x squared plus over 2 plus 21 over 2. And I'm going to anticipate what my next step is. So the idea is I've got a fraction with my y in my denominator. So I want to make the right side into a fraction with like terms. All right, so in this case, I'm going to find a common denominator here, and I get 21 minus x squared over 2 is equal to that negative 4 over y. And so now, when I cross multiply, I get y times 21 minus x squared equals negative 8. And I can easily solve for y by dividing by 21 minus x squared. So y equals negative 8 over 21 minus x squared. And that's our particular answer, the particular solution to this problem. Again, you can solve by plugging in x is equal to 5. All right, when I plug in x is equal to 5, I get negative 8 over 21 minus 5 squared. All right, which is negative 8 over negative 4, which is equal to 2. I didn't show this on the previous example, but I want to show you really quickly what's actually happening here. So in this case, I graph the slope field negative xy squared over 4. All right, you can see right here. And then the particular solution y equals negative 8 over 21 minus x squared. And you notice it goes through the solution 5, 2, if I were to highlight that point right there. Okay, so it goes through the solution, and you can see that it follows all the slopes that we want it to follow right here. Okay, so here's our particular solution that we found with this condition. Okay, our last example, use separation of variables to solve y prime, or dy dx in this case, equals x squared times y, when y of 0 is equal to 4. So 4 steps that you want to do to solve. Well, the first step is really separate, and notice that this can be rewritten as dy dx is equal to x squared times y. And so when we separate, what I'll do is I'll multiply both sides by a dx, and then divide both sides by a y. And so that leaves us with dy over y equals x squared dx. So I've got my dy and y's on my left, my x's, x squared, and dx on my right. Now when I integrate, I'm going to get natural log of the absolute value of y equals x cubed over 3 plus c. And it's going to be a very special case right here because of that absolute value that we get with this unusual antiderivative that's crucial to what we do in a lot of calculus. So in this case, yes, we can go through, let me go back really quick, but we can go through and we can solve this in the same way by plugging in our initial condition. There's nothing wrong with that. There's actually a quicker way to do it to take care of the absolute value and the natural log all in one step. So this is what I'll call the special K condition. All right, so in this case, all right, what I can do is I can raise both sides to the e power because e to the natural log of absolute value of y will just give me the absolute value of y. And when I do that, all right, I get e to the x cubed over 3 plus c. All right, so what I did was I exponentiated. I raised e to the whatever power on the left and the right. One way that I can rewrite this is as e to the x cubed over 3 times e to the c. All right, so remember when you add it within an exponent, all right, you can separate them by multiplying with the same bases. These are just our exponent laws from algebra. Okay, and so on these natural log problems, whenever you see that absolute value of y, we can make our life easier by introducing a new variable which we'll call k. And the k we're going to define in a particular way. We're going to say k is equal to plus or minus e to the c. And it'll allow us to figure out instantly based on our initial condition whether we need to make it positive or negative. And we'll not even worry about what's happening with the absolute value because the k part when we solve for k would automatically take care of that. So thus, e to the c and the absolute value part just becomes y equals k times e to the x cubed over 3. Right? The plus or minus kind of addresses what's happening with the absolute value, and the e to the c becomes the k part itself. So now, the easy thing is we just use our initial condition. And we knew that y of 0 is equal to 4, so I plug in 4 for y, and 0 for x, and I get k is equal to 4. Okay, so in this case, we have solved right away, and because we knew our initial condition was positive, that allows us to make k equal to 4. All right, once we got that all solved, all right, we can solve for y. So k is equal to 4, and y is equal to 4 e to the x cubed over 3. So right away, you've avoided some messy issues that you might get if you try to go through and try to find out what k is, or what the c is if you were to solve the initial condition initially. So in these cases where we see natural log, we're going to want to try to use this k method because it's going to take care of that absolute value and deal with messy exponents all in the same step. So finally, just so you can see what's going on here, we've actually got a pretty funky slope field going on here. This dy dx is equal to x squared y. And what you actually get is this y equals 4e to the x cubed over 3. You see it goes through that initial point 0, 4. All right, and it's got this weird like cubic looking thing going on right around 0, 0, 4, and then it looks like an exponential everywhere else. So this graph goes right through the appropriate slope fields. You can see it matches right here, and the reason why it doesn't match or doesn't look like it matches is because you got horizontal slopes all right around here. So it's like going really, really slow. And eventually these slopes are actually really not, they're not zero, they're like slightly positive. All right, and then you just continue to grow and grow and grow, and you follow the slopes. And sorry, there was a typo right here. So the original problem is y prime is equal to x squared y when y of 0 is equal to 4. Well, let's summarize. That was a lot. Solving for a solution to a differential equation can be done using a technique called separation of variables. So we separate our variables into x's and y's and integrate both sides. Initial conditions are helpful for determining what we call particular solutions. And in cases involving natural log of absolute value of y, we're going to use that constant k is equal to plus or minus e to the c. More on that in class. And yes, you will need to write that if this is a technique that you're going to use. And we'll see you on the next video.